Good afternoon, everyone. Very excited to see this many people attend this panel. My name is Andrew Lin. I'm a first-year MBA student at MIT Sloan. I'm very excited to welcome you all to the workshop series at this year's conference. It is my pleasure today to introduce Momin Ghaffar, Manager of Strategic Research and Development at the Jacksonville Jaguars, and Victor Lee, Advanced Analytics Developer at the Jacksonville Jaguars. They are here to present our topic, Introduction to NFL Player Tracking Data in R. And with that, I'll let them take it away.
Thank you, Andrew. All right, day 2. Welcome, everybody. We hope that this is going to be an awesome workshop and that everyone learned something really cool or something new today. This is going to be a very hands-on workshop, and so for all you folks with laptops, I want you to go to that tiny URL link and download the workshop materials, and we'll give everyone like 30 seconds or so to do that.
You can start with introductions, yeah. No thank yous.
Go to that, yeah. Thanks. And when you're opening up the script, because some of the packages will take a little while, we want you to go ahead and install those packages. And for anyone that's unfamiliar with R, there's that one little line of code that you can do to get all the packages that you'll need for this particular workshop. You can also, in the R console itself, if you're really old school, you can click install and then look up the particular packages. Both are good options.
And in this tiny URL, there's a PDF of this if you need to find that link again.
All right, so before we get started, we do have to acknowledge Mike Lopez over at the league office. He's been instrumental in evangelizing player tracking data and creating a sense of education around it. And really, we had to look to him for ideas on how to make this workshop as practical and useful as possible. That being said, his Big Data Bowl is sort of the primer for all of this. We're using the inaugural Data Bowl's data set, and we're going to go ahead and go into the nitty-gritty there, but all of that's sort of his baby, and we wouldn't be here without that. And of course, our all of the football player tracking data providers. In this section, we're going to be scrutinizing next-gen stats, and so they're wonderful, and you're about to see some really cool stuff today.
So just some quick introductions. My name is Victor Lee. I went to school just south of here in Providence at Brown, where I studied statistics. I joined the Jaguars in 2017, so I'm going to my 4th season now. And before that, I had previous experience at UCLA men's basketball, and then also Paramount Pictures predicting box office performance.
Victor, I'm gonna have to do a little bragging. This particular Sloan conference has featured very heavily Jeopardy and Ken Jennings. Victor was also a Jeopardy participant, and so the cool fun fact that I think belongs in this introduction. Then for me, I'm just a guy. Joined the Jags over the summer, worked at the San Antonio Spurs, participated in the inaugural Big Data Bowl, went to Duke, and so UNC's going down tonight. For this workshop, we're going to split into 2 parts. So the first part is us just making sure everyone's got a familiarity with what exactly player tracking is, and to sort of demystify what it is. And we'll go into some tips and tricks, things to be mindful of as you're getting your hands really dirty with all that data. And so we'll also kind of show some examples of applications, and Victor's going to guide everyone through a script where you're able to look at particular metrics and visualizations. And so on that topic, right, the structure and format is really not that crazy. You've got this interplay between the game ID, play ID, and frame ID. And the reason why we have a frame ID is because a lot can happen in a second. So I just did a really weird movement, and that was probably less than a second. So the RFID chips that are capturing the microscopic movements of our players is manifesting in that data. And so for each play, you'll see 10 frames worth of data. And so as you can imagine, with a lot of plays, a lot of games, you end up having a lot of data on your hands. And so the other cool factor in all of this to really consider is that we've got the XY coordinates of the ball and players on the field. So all 11 players on the offense, all 11 players on the defense. I won't really go into all the variable definitions here, but the things to keep in mind, especially when we start talking about animations, are the jersey numbers, specifically filtering by things like the play ID. These are all the things that Victor will kind of go into more detail. The cool stuff to keep in mind also towards the top, you've got speed, distance, direction. If you're a fan of trigonometry, you're going to see that you can take a lot of different Euclidean distances to sort of arrive at a very practical way of looking at the distances between players. And as far as tips and tricks go, really we want to hammer home quality assurance. And for those of you already working in sports, or for those of you hoping to work in sports, ultimately the quality of your work matters. And so a really important first step in all of this is just to calibrate your dimensions, right? Data without context isn't going to really make much sense. And so you also want to go and take an isolated play and make sure it lines up with the video. If you're not seeing all of that data, it's possible that someone didn't make it on the field. It's also possible that something's gone awry. And so you want to be able to speak to that whenever something kooky is happening. And then, scaling is just important in general. You don't want to deal with the totality of data available to you if you can start off small and prototype and create something cool after you've seen it work. And especially with mega data like this, it's going to be very laborious to go into the totality of data and hope that you can have a script run in 30 seconds or less. And then in general, from a data engineering perspective, for those of you with SQL chops, having a backend that you can sort of feed into R or Python is going to be way more helpful to you than trying to do everything in SQL or R. And mostly because, and I'm sure someone at this MIT conference can really fight us on this if they want, but you're going to see some sort of efficiencies when you're joining data as opposed to having a for loop in R that'll take longer to run and complete. And because this is an educational conference, we did want to introduce something that we thought was kind of fun. A Cartesian product is something that Victor is going to go into in more practical detail. But when you're joining data together and you're trying to get things like player distances, you're going to want to have a number of players that are related to a particular player that you want to study. And so to do something like that, you're going to join on yourself. And what does that really mean? I think this picture is such an elegant way of explaining that very simple concept, but a concept that we, having really gotten into more detail with player tracking data in the past, have really grown to appreciate. And then as far as applications go, and by no means is this the totality of what you could possibly type of cool data. But for starters, you could go into the R package, NFL Scraper, and look at things like expected points added for a particular play, or the win probability for a particular play. You can see what sort of routes or what sort of passes give rise to higher amounts of expected points, or types of win probability swings as a result of this sort of execution of teams. And so, that's something that's free of cost, it's available, it's not proprietary, and I encourage all of you after this to take what we've done today and find that NFL Scraper package and see what interplays do exist between what happens on the field and what that means in terms of team performance.
And NGS has done a great job of popularizing sort of what you can do with this data. So if you watch an NFL broadcast now, you can see top speeds, separation. They've had that commercial recently where it's Russell Wilson tossing a deep ball, and it's like, oh, it was only a 4% catch probability. That's all from this player tracking data. So there's a bunch of basically spatial components of the game that can now be captured. And this is great in tool development as far as quantifying parts of the game that we previously couldn't quantify from just play-by-play data or a box score. In addition, we can visualize all of this, which is great. So we'll be going through some Voronoi plots, which kind of shows space ownership for each player, and then also some animations of the play, just so you can visualize the play as X's and O's, sort of dots moving around. So this is an example of a Voronoi diagram. So this is the 2017 opening game in week 1, and you can see here, basically, this is that kind of quality assurance. There's this frame at the second and goal play, and then you can see the Voronoi plot. So you can see, on the left-hand side, Tom Brady handing off the ball. You can see the sort of the ownership that each player has of the field. So, you can, as you look kind of into that center area, you can see the hole opening up for Gillisley to score the touchdown. So now we're going to be moving into the R script. So I'll be working kind of chunk by chunk through, explaining as we go along. And Moment will be going around. If you have any questions of just setting anything up, feel free to raise your hand and flag him down, and he'll be glad to help you out. All right. Can everyone see the font on that? All right. Is that good? All righty. So I'll basically be walking you guys through this. Feel free to run it along on your computer as well, but we just want to, I want this to be as broad of an audience as possible. If you've never coded in R before, just follow along, hit run when I hit run on whatever parts I highlight. I'm going to try to explain sort of really the nitty-gritty of all of this as we move through, just so it hits every base we can. So again, big thank you to Mike Lopez. Some of this code is adapted from Mike Lopez, and all of the data that we're using is hosted by him on the NFL League Office's GitHub. So like Momin mentioned, this is from the first Big Data Bowl, and there's one game left of data available online. So we have to use publicly available data, so this is kind of what we're going to use as our test set here. And these URL links link to the data itself. It links to some descriptions of the data, and it just has some interesting code snippets that are helpful, just extra resources as you work with, familiarize with yourself with this data. So let's hop right in. So first, we're going to load all of these libraries that were in that first slide. So we're just going to be using functions from here. And once that's loaded in, I'll be just collapsing these code chunks as we go along, just an easy way of organizing through. So the first thing we're going to do is we're going to load in all of this data. So my apologies. So we're going to load in all this data. And because these CSVs are hosted on GitHub publicly, we can use the reader function and using the read CSV function from the reader library to load in basically these URLs to these publicly hosted comma-separated value documents. So there's going to be 3 files that we load in. One is the actual tracking data itself, and the other 2 are sort of provide contextual information. So one is game data, and then the other is plays data. So is the feedback okay back there? Okay, so we're going to run these 3. And what this will do is create 3 data frames in R. And data frames you can kind of think of almost as like matrices that hold data. We'll be able to view them in R very nicely, kind of view them almost similar to an Excel spreadsheet. So this is kind of a classic rectangular data frame, very even, but there can be missing values and stuff, which we'll be working our way through. So as we can see here on the right side in RStudio, for those that aren't too familiar, in this environment here, we can see basically everything we've loaded in. So for example, we had 3 different strings assigned to these file underscore name of the data, and those are the URLs. And then we have the actual data frames of the data we loaded in. So I want to give you guys sort of a dive into my brain. When I get a new data set, how do I approach it? How do I look at it? How do I figure out what's going on and make sure I know what's going on before I actually just start running analyses on it? So first thing I do, I just want to know what the data looks like. So let's first look at the plays data and just see what's going on, what it looks like, as if you're opening an Excel spreadsheet. So using this view head plays. So head plays just means get the first few rows, and view opens up this very Excel-like GUI of RStudio, which is a really great, helpful part. So we can see here in this play data that we have game ID, play ID, which was mentioned. It's going to be sort of our ID to allow us to join information on. And then various contextual information about the play itself. So game clock, down and distance, Some interesting ones here to help you do splits later is offensive formation, whether they were in 11 personnel, which is 1 running back and 1 tight end, or 12 personnel, 1 running back, 2 tight ends, for example. So, interesting ways you can split the data through. And other things of interest, so defenders in the box. So for run plays, they always talk about, you don't want to run into loaded boxes. You can see the personnel and defense, right? So 5 D linemen, 2 linebackers, and 5 DBs. So they're in a nickel package, which seems to be the base package nowadays, but you can also see that, say, this play is in a base 4-3, for example. So all of this data is useful for basically, once you have processed player tracking data and you want to then turn that into insights, you can bring this game information to help contextualize it. And now let's do the exact same thing, but with the games data. So back then, the previous data set was all at the play level. This is going to be at the game level. So now we have information on the game itself. So when was it played, the ending score, the resulting score of it, the teams that were playing. An interesting one is the stadium type, right? So maybe you want to compare games that were played outdoors versus indoors. You can also append on weather variables, right? So maybe looking if a quarterback plays better in good weather versus rainy weather, for example, or if some players just play the same in both temperatures. Humidity, wind speed, if that affects throwing game and that kind of stuff, wind direction. So bunch of stuff here, again, just to help contextualize any information that you glean away from the player tracking data. And lastly, we're going to look at what the tracking data looks like. So this is going to be what we're primarily going to be working with today. So we have a timestamp on every single frame, and then an XY coordinate, speed, distance, direction is 0 to 360, kind of going in a circle where 90 degrees is facing an end zone and 270 is facing the other end zone to help get player alignment. We have event, so every frame doesn't need to have an event, but the frames that do have an event, say in this case, at the 5th frame for Anthony Sherman here was the kickoff, the moment the ball was kicked off. And then some important things to take note, NFL ID is super useful here, basically to help identify the player that's being tracked. Another important ID is frame ID. So this just helps you keep track of which frame in the play you're in. So every play will have frame ID from frame 1 to however many frames there are in that play. And then game ID and play ID as well. So let's just do really quick basic plot of just one frame in one play. So let's look at that opening kickoff play, and here we're using ggplot. I'm going to show things in both base R and sort of tidy kind of R style, so just to give you a taste of both. It'll be different styles as we move along through, but just to show that there are multiple ways to do the same thing in R. So here we're taking the tracking data, tracking full, and filtering it based on a play ID, and we're just looking at the first frame on that play, and then we just want to plot X, Y, and we're going to color it by the team, so away team, home team, and just plotting all those points. And we'll see here, it looks like a kickoff, right? So just the normal kickoff formation. You got the away team, which in this case is the Kansas City Chiefs, and the home team, which is the New England Patriots. And note that there's also a green dot right there, which is for the ball. So easy to forget sometimes that the ball is also being tracked. So there's really 23 points per frame in each one of these plays. So now I'm just going to do some quick hitting functions to basically, this is what I do when I get a new data set, just to get an idea of what I'm working with. So first thing, what's our rows and columns? How big is this data? So using the dim function, we can see it's just over 300,000 rows and 14 columns, which in the case of player tracking data is a very small data set, because you can imagine this is just for one game's worth. If you add multiple games in 1 week and then over several seasons, then it really, really adds up. So how do you check that there's only one game? We find the unique game IDs and find how many unique game IDs there are in this data set. So in this case, there's one game in this data set. And then how many plays do we have? So same thing, but instead of game ID, we're going to do play ID. How many unique play IDs are there in this data set? looks like there's 177. So 177 plays that were tracked with this tracking data. So Momin mentioned quality assurance. So sanity checks, always super important. So the first thing I want to check, in an NFL game, there's usually 22 players on the field unless something went really wrong. So we're going to look and just see how many players are there for each play in this data set. So this is not using the tidy kind of format of R. This is using base R, using the aggregate function. So we're aggregating NFL ID, which if you remember is sort of the player ID, based on every play. And the function we're doing is the same function that we did in the line above. We're doing length unique. So find all the unique, in this case, NFL IDs, and then find how many there are for each play. So checking this out. So we see a bunch of 22s, good start. And just a visual check. Similar to Excel, you can sort things. So by clicking this, you can sort. And it looks like, bunch of 22s, but there is one play that only has 21. So I'm not gonna dive into, how to fix that, but this is just a good way to check. You can then go and spot check, was there only 21 players on the field for that play, or did maybe one of the tracking points was not tracked during the data collection? So if you guys remember, I pointed out that events column where there's a bunch of NAs, but in the first thing I showed there was a frame where the kickoff was tagged. So let's just check out what kind of events there are. This is gonna be really useful for helping to slice our data if we wanna look at just the kickoff time or maybe just when the pass was thrown. So using this is just a really sort of base R manual way to look at. I basically you table all the different events, which basically finds the count of each event in that column, and then just sorting it to see what's the most common. So it makes sense, every play starts with a ball snap except for kickoffs. First contact, tackle, pass forward is like the frame in which a pass is thrown. Pass arrived is the moment the pass was arrived, whether it's complete, incomplete, intercepted. And you get to some kind of less frequent ones. So, a shift, when a punt landed, when a QB kneel, pass tipped. So there's all these different events that help you sort of demarcate what's happening frame by frame as we go through this data. And as you can imagine, there are multiple events on one play, so we can see, all the different sort of combinations of events that can happen on a play, at least in this data set. So again, we're using that base R aggregate function where we're aggregating event and play ID, events based on play ID. So we want to see what are the unique events on each play ID in this data set. And just to note that this works on this tiny data set. If you ran this for a whole season's worth, it's probably just going to crash R. So this is just kind of a good way just to check a small subset of data. So we can see here. Let's actually, I'm going to venture on the terrifying world of live coding. But there we go. One for one. So here we can see, play 44 was that first play we looked at, which was the kickoff. So we can see there was kickoff, kick received, first contact, tackle. So it makes sense with the way we intuitively think about football. But, for, say, pass plays, we can see how the events are tagged for the different plays, so we know when we're filtering by these events later, how we're actually filtering and what plays we're filtering in and out. And the other part of this quality assurance is checking our missing values. So using this, isNA basically tags all the NAs, and if there's an NA, it spits back true. If there's an actual data value, it spits back false. And then we're going to find the column sums, so really how many NAs are there per column, and then we're going to sort that by column. So we can see a bunch of NAs in event, which makes sense. Not every single frame that's captured will have an event. And then we see an interesting thing here where there's exactly 13,743 rows that have an NA, an NFL ID, jersey number, and direction. So that's a little weird, and let's just check out what's going on there. So here, I'm going to be finding all the rows that have an NA and NFL ID, and aggregate their display names to see maybe there's a pattern there. And running this, we see the display name's the football. So someone can forget the football's there. And in this case, we want to work with just the player data. Obviously, you can keep the football data for other things, but this is just, for the purposes of our discussion here, we're just going to work with player data. So this is a base R way to learn how to subset data. So which rows that have the column display name does not equal football. So we want to take all the rows that don't have the name football. There's obviously a much easier way to do this with tidy, but just want to also show it in the base R fashion. And we're going to store this in a data frame called tracking, and that's kind of the data frame we'll be working from here on out. So this is just a good best practice where you don't want to be modifying that initial data you have in case you want to go back and say, get that football data again. You don't have to reload in the original data set. So now we have tracking, and let's check out the NA count again by column for just this tracking file without the football. So again, bunch of NAs in event, totally makes sense. We got rid of that weird 13,000 NAs because we removed all the football rows. And the last thing is we have now this pattern of 27 rows that seem to have X, Y, speed, distance all wrong. So my first hunch is, maybe like there just weren't tracking coordinates for those 27 rows. So let's check that out. Here we're looking at all rows that don't have an X, an NA in the X column. And we can see here that seems like all of these rows are missing all of those columns that had missing values. So in this case, those really don't have any use for us. Obviously, for quality assurance purposes, probably have to go back later to figure out why those NAs are there, why we were missing those points. But for our purposes, we can just remove those rows. So again, we want to find all the rows where, so is.na will spit back true if it's NA, but the exclamation point is basically not. So the opposite of true is false, so we want to take all the rows that have data in the X column. And now one last check of the NAs. Beautiful, bunch of zeros, and then just the NAs in event, which again, well expected. So I'm going to close this code chunk. So now we basically have what I would call a clean data set to start working with. This is kind of, it's a grind. It's nothing exciting, but it's super important as we go into actual analysis and metric building using this data. So let me just collapse this just for visual ease. So in this workshop, we're going to be creating one metric, which is basically on a given play, at a given frame, what is the player's nearest opposing player? So for example, on a handoff, Mike Gillisley's getting the handoff. At that moment of handoff, where is the nearest defender? Who is the nearest defender, and how far is that nearest defender away from them? So really basic metric, but something that can't be captured in a box office or a play-by-play, and we can get that for every single frame, so we can see how that changes over time. There's a bunch of analyses you can do with just this one very simple metric. So we're gonna go and find out how to calculate this metric purely in R. So one thing to keep in mind with all of this is that we're doing everything in R. There's a bunch of pre-processing you can do if this is in a SQL database. That'll make it a lot easier, a lot less of a hassle. It also can just be a lot slower in R. Like we mentioned before, you don't want to do a for loop through every single row. If you imagine here, we have 300,000-ish rows, and that's just for one game. And doing a for loop through that and doing intensive calculation every iteration that for loop can really, really add up the time. So we're going to be leveraging that Cartesian product by joining itself, doing self-joins. But again, you can speed up this process by doing SQL pre-processing or by using some special spatial data packages. So in the comments here, I mentioned some of the spatial data packages such as SP and RGeos. So those packages were built to work with this kind of XY time data really efficiently. Just for this purpose, I want to show it using just base R and tidy as well. But if you want to look for more efficient ways to process, those spatial packages are definitely a good place to look. So, as Momin also mentioned, we always want to work with a small subset. Because this data is pretty similar play to play, it's just x, y coordinates moving over time. If we can get a data process to work on just one play, it's going to work on pretty much every play in this data set. So what we're going to do first is we're going to just look at one frame on one play, in this case that kickoff, and try out sort of our data engineering on that. If it works out great, perfect. Let's expand it to this entire data set, every frame for every play in this data set. So this little subset we're going to work with is the opening kickoff, which I'm going to store into a data frame called short for KO, kickoff. And we're going to basically find play ID 44, which is that first play ID that we've been looking at. And we're going to take the frame at which the kick was received. And the second part is basically all of the columns that we're going to want to pull out from there, and then we'll be able to use in our analysis. So we want the X, Y coordinates, we want the NFL player ID, the name of the player, game ID, play ID, frame ID. So getting all those IDs will be important just to keep track of which rows are which, and then the team they played on. Because remember, we want to be finding the nearest opposing player. We don't want to be finding the distance to their nearest teammate, for example. So using this, we'll subset it, and then we can just take a quick look at what this looks like. So we have 22 rows, which makes sense because we just have one frame, so one row per player on the field. And we have a player, their XY coordinates, their bunch of IDs, and then which team they're on. For example, Anthony Sherman was fullback for the Chiefs on the away team in this case. So like I mentioned, sanity checks every step of the way. So first thing, let's make sure there's 22 rows. So n row calculates how many rows are in the data frame. 22 rows, perfect. Next thing, we want to make sure we capture that team variable correctly. There should be 11 on each side of the ball using base football knowledge. So there we go, 11 away players, 11 home players on this frame. So now I have two different ways to plot basically the same thing. One using the base R plotting, which I use in just kind of my day-to-day because it's super quick and super ugly, but it gets the job done. And then also using ggplot. So this is just plotting this subset, that one frame when the kick was received on the kickoff. So first using base R, margins are too large. All right, let's just move on because I'm not going to be debugging on stage. We'll just skip to ggplot, which is the much prettier plot. So similar to that first plot I made, but this time without the football. And we can see, very similar. Like it looks like what a kickoff looks like when it's being received. The wedge is forming. The formerly allowed wedge is now forming in front of the kick returner. Some players have made it downfield. Some blocks seem to have already been engaged. So just a good sanity check to make sure everything looks like football. So the first thing we want to do is create a new variable that basically, if a player is on the Chiefs, their variable in op team will be the Patriots or the home team. The reason for this is allow us to do that self-join on itself to find that Cartesian product because we want to be joining a Chiefs player onto all of the Patriots players, for example, and because we want to find the distance between opposing players, not teammates. So just using a simple if-else statement. So if the team is away, that variable is going to be home, else it's going to be away. And another very sanity check that variable creation was correct, logic worked. We're going to find all of the rows where the opponent team equals the player's team. And in this case, it should be none of them, right? Because we're always finding the opposing team. So this is where we're going to get into that self-join, that Cartesian product. So the idea here is that we have this KO data frame with one row for every player. And what we want to do is we want to be able to do column by column math to basically find distance using XY. So kind of XY of Anthony Sherman, but we want to find the XY of the 11 other players in relation to Anthony Sherman. So when we do a self-join based on team and opposing team, this will basically expand out our data frame. So Anthony Sherman will get 11 new rows where it's him paired with all 11 other Patriot players on the field. And then we can do that column by column math. This is kind of our way of getting around using that for loop. And it's in R way faster to do this kind of vector addition, division, multiplication. So we're doing this inner join. We're basically left joining KO onto itself. But note here that the variables we're joining on game ID and play ID, which makes sense. We want to just make sure we're getting the same game and same play for every join. But we're joining the team variable onto opposing team. So that'll allow us to get that expansion for 11 rows for each player. So let's run that and see what KO join looks like compared to KO. So if you guys remember, KO had one row for each player, while KO join has 11 rows for each player. So in this case, we have 11 rows for Anthony Sherman, and each row corresponds to a different Patriot. So, Anthony Sherman with Dion Lewis is a kick returner. And note that we have the XY coordinates for Anthony Sherman and the XY coordinates for Dion Lewis. Now we can do kind of just like in Excel or something, just column by column math to help find the distance for each one of these rows, each one of these opposing player pairs. And that's what we're going to do right here. So this is just the distance formula, normal Euclidean distance, just to create a new column called distance. So running that, and then we can just do a quick summary to look at our distances. And makes enough sense, It'd be really weird if you had a distance of like 1,000 yards. All of these units are in yards, so if your max distance was 1,000 yards, something went wrong. Also, the way we set up the Euclidean distance formula, everything should be a positive distance. We're not capturing direction. We just want the magnitude between two players. So now that we have this data frame that has, let me expand this up. The distance between every player pair for every time in the play, we want to find what the minimum distance is, and we want to just capture that row. So just looking at Anthony Sherman here, it looks like Brandon King has the smallest distance at 2.7 yards. So what we want to do is we want to roll it up and go back to our format where we only have one row per player, and then the only row that is with the opposing player that has the minimum distance to them to find their nearest opposing player. And the way we're going to do that is now we're going to start using some tidy stuff. So this is kind of where we use pipes, where you can imagine you're taking a data frame, putting it through a function that modifies it, taking the output, you can then pipe that and put it through another modification, going so on and so forth. So in this case, we're taking KO join, we're grouping by display name, game ID, and play ID, and then we're slicing it, which means we're only going to take specific rows. We're going to slice it based on whichever row has this minimum distance for that player. So running this, we're going to roll that back up to a data frame of just 22 rows. And this just renames to help make things a little clearer. So names KO join. And let's view KO join now. So now we have Anthony Sherman, just one row for Anthony Sherman, and his nearest player, Brandon King. The nearest player is XY coordinate, and then the distance. So you can kind of see we had the original, we expanded it to find all the distances, and then we roll it back up to get the variable we want. So this worked for one row, awesome. This is going to be the only time I run something before explaining it, but I'm just going to run this part because it takes a little bit of time. And I'll explain why I need to run it early and how to avoid having to run it early. So now that we found out that it works for one play, we want to do that. Found out that it works for one frame. We want to do that for every frame on every play in this data set, which you can brute force, which is what I'm doing now. Not the best practice, but you can basically loop through every single frame on every single play and basically apply what we just did up here, just generalized into a for loop. So in this for loop, we're cycling through for a given play ID. We cycle through all the possible frames in that play ID. So really, the first iteration of loop will be the first frame in the first play, and then once that's done, we're going to go to the second frame in the first play, so on and so forth. So again, it's a very brute force method. This is why doing all this processing just in R is not the wisest, especially when you have a big data set. Sometimes it's the only way to do it, in which case you only have to do it once and then store it away in your data frame. Store it away in your database where you already have that variable built. If you don't have a database, store it in a flat file, a text file. But it's just kind of a thing that can always be made more efficient, and really you have to, for your purpose of whatever work you're doing, you got to realize, maybe I can just brute force it and just suck up the 5 minutes of waiting for it to run. Sometimes that's not possible. So I've timed this to run just for maybe like about 4 minutes, but while we wait for this to run, I just want to open up to any questions. Just if anyone, super lost, as any question possible, just for a couple minutes as a break in this Q&A. So yeah, right over there. Yeah, so with the SQL pre-processing, it's basically doing similar things like this, doing these inner joins in SQL, where SQL is basically built to do this, so it's much faster to do it in the sort of SQL environment. Also doing something like rolling calculations in SQL helps this out a ton. In this R environment, probably the fastest way is doing that column by column math, but in the SQL environment, doing something like rolling calculations really speeds it all up. Yeah.
How did you choose to use R instead of something like Python or another language?
Yeah, so to be perfectly honest, I was just trained in R. So R is just kind of my bread and butter language. Totally do this in Python. Pros and cons as far as speed and efficiency in both. I know in R, like doing the column math is like way more efficient. So really just whatever you're comfortable with. I'd say in our work, we probably do 50-50 R Python, just depending on who's working on it and then what kind of projects we want to do. Often data processing is a little easier in Python. One thing I like about R is that we have access to these spatial packages. So in these spatial packages that are built specifically for R, it helps you work with this data a lot more efficiently. Yeah, right there in the back.
What's the accuracy in X and Y direction?
Right, so it's accurate. I don't know, I can't give an exact number, but it's accurate to a few feet. And basically, the data is smoothed out and interpolated a little bit, just so if you were to sort of animate and plot the point out, it doesn't look like they're jagged, sort of like jiggling around, and there's that sort of noise there. So there is a little bit of interpolation and smoothing in that accuracy. Yeah, right there.
Do you have labels for the plays that were called by the coach or coordinator for all these for every play in the data frame?
Right, so if it's our own data, then yes, we do have our own, say like we can tag, say coaches and pro scouts would be tagging these plays and we can line them up. Those aren't provided by the league, for example, because you aren't submitting your play calls to the league. But that's kind of where it's really important to bring in this data and attach it to sort of existing scouting platforms to know, yes, that play was 11 personnel, but was it trips cluster? Was it more spread out? Was there a wing back? That kind of stuff. So just to add more detail and information to that play. Yeah, in the blue.
What kind of techniques and tools do you all use to present this to like the coaching staff?
Yeah, so once we process all this data, so you can tell I've been doing kind of just these basic GG plots. That's really just for myself, just to sanity checks. That's why I often do base R plots, because it's super quick. No one else is going to see it besides me. But at least at the Jaguars, we primarily use Tableau as our visualization method, whether that's a live dashboard that we're automating and feeding new data into, or just building nice, pretty visualizations. It's just a really easy way to build great visualizations in a matter of seconds. So that's kind of how we visualize and build reports out. Yeah. Sorry, there's a mic. I can't hear you.
Sorry about that.
All good?
The project that you've provided us with is kind of a walkthrough. How long, in terms of time, does it take you to make this and work through something like this? A day, a week, longer?
Yeah, so I would say actually the most time-consuming part of all this is figuring out what metrics to build in the first place. Something like this is a pretty fundamental metric, right? Just kind of useful for maybe, in a wide receiver reception model, what's the probability of them catching it? You probably want to know what their distance is. We're actually going to touch that really quickly right before we wrap this up. But really, once we get into the more advanced metrics we want to build, it's really picking which metrics we want, figuring out, is that even going to be useful once we create it? And then once we get that, the method of actually doing the math, pretty much the same framework. You're just kind of doing different calculations on the different relations between dots on a field over time. So really not that long. This is like, a couple hours and just making sure it's clean and presentable to you guys. So yeah. So it looks like this finished running. There will be questions. I'll save time for the end as well, but just wanted to touch in with you guys now. So we have this data set of basically finding nearest DF, which in this case is a map between a NFL ID for every game, for every play, and for every frame in that play. For every player, we have their nearest defender. So for example, on this frame in this play, in this game, the nearest player with player ID their nearest opponent is Marquise Flowers with a distance of 18 yards and their coordinate. So using this, we can join this on to our original data to basically find this new metric of distance to nearest opposing player, which we're going to do right here. So we're just joining on that nearest DF, which will bring on all those new variables of nearest opponent. And let's just check out the first 20 rows of that to make sure it makes sense. So we have Anthony Sherman across all these different frames and the nearest player to Anthony Sherman on all those plays. So it's Marquise Flowers, but then it changes to Jonathan Batamosi, and we have the coordinate of the nearest player and then the distance. So we can see the distance sort of closing as the kickoff teams reach each other. So let's collapse this, and I just want to show you guys, we have that variable now. Let's just do a quick little exploration. So this is a super relevant variable for whether a catch can be made, right? Our intuition is if a player is wide open, they're much more likely to catch a ball than if the player cornerback right on their back. So what we're going to look at is basically at the moment the ball was thrown, how many yards of separation did the targeted receiver have from their nearest defender? And then look at just the split between complete passes and incomplete passes. So first, we're going to join on that plays data frame, which if you guys remember has all that information on a play-by-play level. And the variables we want from that are which team has the ball, the length of the pass, which could be useful, the result of the pass, which we'll be taking complete or incomplete, and then play description, which is a play-by-play. And I'm going to be doing a regular expression to basically pull out who is the targeted player on that play. It's a little complicated, but I just want to give a hint of the regular expression, which is useful for pulling strings out of, text out of strings. So let's run this and then look at the different types of pass results available. So they're abbreviated, so C is caught, I is incomplete, R is a quarterback run, and then S is sack. So the different kind of outcomes of a passing play. So first, I want to track basically which players are on offense. So in this case, we're doing a nested if-else. Not the prettiest way, but just a way to do it in base R. You can also do this in the tidy format. So if the possession team is New England and the player is on the home team, which in this case is New England, we're going to give them a 1, else 0. The opposite case is Kansas City and away team. So this will basically help us flag which players are on offense. And now we're going to filter. So we want to take just the passing plays where there was a completion or incompletion. So we're going to get rid of all the sacks and runs. And then we want to take just the frame at which the pass was released. So using this tidy format, taking the tracking data and filtering it based when pass result is either C or I, complete or incomplete, at the frame in which the event was a forward pass was being thrown, and we're just taking the offensive players because we just care about separation for the targeted receiver. So doing this filter, we'll see here that pass attempt has 737 rows, so 737 coordinates. So a little short on time, but just want to run through. I'm not going to get into the full details of this regular expression, but basically what we're going to do here is if we look at, in pass attempt, the different descriptions of the plays. So we can see one description here is Tom Brady, pass short, left to targeted player. So what the regular expression does is it captures where in the string the word pass and the where in the string to is, because that's the same pattern in every pass play. And then we want to capture basically the last name of the targeted player. So there's plenty of great websites out there to explain regular expressions. Also love regular expression calculators, which you can put in a string of text and then test out different regular expressions to be able to pull out the string you want. And in this case, we're just going to be pulling out the targeted player and then also flagging the rows in which the coordinate is the player that was targeted. So let's check out what that looks like. Oh, this mouse is not cooperating. So we can see here on the Burkhead play, the targeted player is Burkhead, and this one row that's flagged 1 is Rex Burkhead. So using this, we now have who was targeted on the play, and then we can filter this. So basically pass result, we're just going to rename this C is complete, otherwise it's going to be incomplete, just to rename it for our visualization. And what we're going to do here with this ggplot is basically build a box plot for completed passes and incomplete passes. What was the distribution of targeted receiver separation from their nearest defender? So it looks like it makes sense. You're a much higher chance of getting a complete pass if you have more yards of separation than less. So it looks like for plays that there was a completed pass, there's a median of about 4.5 yards of separation, while on incomplete passes, it was about 1.5 yards of separation. So again, this is just for one game, but this is just an example of kind of a cursory exploratory analysis you can do with this kind of metric created by NGS data. So now I'm going to hand it off to Momin. He's going to be going through animating the data, and we're just going to do a couple quick visualizations to wrap this up.
And I know I got to a handful of you. If you have questions after the session, feel free to grab either of us. We'll make sure we debug the code with you. And because we are running a little short on time, I'm going to try to breeze through this. What we have here, or what we're about to do, is animate the kickoff for this Pats Chiefs game. We're going to go ahead and feed in the specific play ID and have that stored. And you see commented out in this code here is are two other play IDs. One's for a Travis Kelce touchdown and the other is for a Gillislee touchdown. You can put those in on your own time and see how those plays end up working. Specifically, line by line here, what we're really doing is just pulling in a subset of data specifically for that specific play ID. And as we run this, what we're really doing is creating the specific field dimensions. We're really just looking at the geometry of this particular play so that we have a basis by which we can kind of bound this play. For those of you who are ggplot experts, this will be very familiar to you. For those of you who are not, what we're doing is taking what we've been given in previous encounters with Mike Lopez at the league office in how to specifically set up a play animation. I'm going to run through all this code. And I know this can be a bit overwhelming. We can sit down with anyone who's got additional questions, but really the call-outs here are the various, essentially, arguments or parameters you're passing through to be able to get this animation to work. And you see things like these pound sign numbers. These are just color codes. We're getting the color codes for Patriots and Chiefs players. I'm going to go ahead and highlight all of this. This does take a little bit longer to run, and so we definitely want to leave at least like 5 minutes for a Q&A. And so I'm going to go ahead and highlight all of this and ask you to train your eye on the bottom right-hand quadrant of my screen so you can see what happens. So the kickoffs occurred, returners about to get walloped. Pretty cool, huh? You can do this for a number of different plays. I guess just very quickly, if you really wanted to, you could plug in 938 for that Kelsey touchdown and 345 for the Gillisley touchdown. Victor's going to finish this code walkthrough with the Gillisley touchdown, and I'm just going to animate it real quick so you guys can see what happens.
So while that animates, just the next thing we're going to look at is those Voronoi diagrams, which kind of shows space ownership. So basically, looking at all the players as they relate to each other, who kind of owns the space around them. The easiest player, kind of which chunks of grass a player can most easily get to, we would call it like they own that space. Borrowed ideas from soccer and more spatial sports, but very relevant in football as well, as you saw with the player separation. So in this case, it's a Gillisley touchdown, and you can see he hits the hole and scores the opening touchdown of the 2017 season. So we're going to look at this Voronoi diagram, and we have about 5 minutes left here. I just want to run this, and just to show you an idea, Voronoi diagram is much simpler as far as ggplot than an animation, so we're just filtering on play ID, frame ID, which is we're just going to look at the point of the handoff, which in this case is frame 28, and we're going to look at just the plot without the Voronoi. So looks like it makes sense, right? You have the ball, Tom Brady handing off to Gillisley, you have linemen blocking, you can see the hole forming. So we don't get the Voronoi sort of land ownership around that. And we can do that using basically this stat Voronoi in ggplot, which draws the polygons around the space that they own. And you can plug in any sort of play. ggplot's great because you can change all these different parameters, but this is our Voronoi example, so we can see, dimensions are a little weird, but you can see that the players in blue, which are linemen blocking for the Pats, are owning a bunch of space in the hole that Gillisley can then hit and easily score the running touchdown. So with that, just again, wanting to thank everyone here at Sloan, Mike Lopez of the NFL, the Jacksonville Jaguars. It was really a pleasure and an honor to be here, and just wanted to open up for Q&A for the last few minutes. And there will be a microphone being passed around, so just raise your hand.
Do you have information on where a player is looking, like the heading of them as well? Because like with this, who owns what space would be a lot more relevant if you knew like where they're looking or where they're pointed.
Right, yeah, so we do have the direction variable, which is that 0 to 360 degrees, kind of like polar coordinates almost. And you're right, that is extremely important in a Voronoi diagram to basically, it's much easier for you to own space in front of you than behind you. So kind of creating a topographical map on top of this Voronoi where maybe you own more space in front of you and then less space behind you, for example. So yeah, we do have that data. It's very useful.
What do you do to handle missing data points?
Yeah, so there's a number of ways. One, sometimes if it's just like missing a frame, random frames here and there, it's not the end of the world to sort of interpolate and just find, the median point between the two data points you have around that. If you're missing much more data, like whole plays, for instance, then you're in trouble. That's kind of where you have to realize, the limitations of we're capturing this physically during a game, so maybe weather is affecting it, and that's just data that we can't capture, which may be able to be filled in the future with computer vision, for example, taking a broadcast feed instead of the raw tracking chips on the data, on the players.
a data scientist unfamiliar with this data might be inclined to impute certain values, given the type of data that you're working with here, that probably doesn't make the most sense. So as Victor alluded to, the technology is improving. Where we were 5 years ago is drastically different from where we are today. And so we'll be rectifying those sorts of data inconsistencies as we move forward in the space.
First thing I want to say thank you. This was wonderful. Really appreciate it. When you move this sort of stuff up the food chain, do you find that the people who are the stakeholders as far as coaches, players, et cetera, are they interested in Voronoi diagrams, or do you present that in conjunction with? I didn't realize that was that funny. Do you present that in conjunction with video, or what? When you present, how do you find this best to move to the people who are most interested in it?
Right, so that's a super important question. What's the point of all this if no one listens to you? So one big thing is just figuring out the learning styles of people consuming this information. Some people might love these Voronoi diagrams to see the visual. It's always great to attach it to film. Like in the deck, we had a screen cap of the handoff next to the Voronoi diagram, and you can intuitively be like, oh, that lineman owns that much space, and then look at the Voronoi diagram and like, okay, that lines up, it makes sense, the math checks out. It's always really important when creating these metrics to be creating metrics that are going to be useful, right? There's no point in measuring something if that's worthless to a scout, for example. So it's always great to hear how a scout looks at a player visually and then figure out how can we capture that in the data doing different sort of analyses and say finding nearest opposing player. So it's always important to have that dialogue back and forth from what your deliverable will be and then how you'll get to there. This will be our last question. Seems like wrapping up on time.
Hi, I was curious can you extract those areas from the Voronoi plot, or is it part of that package?
Yeah, it's part of that package, and you can extract that area of just actual like square footage. Then you can apply weights, like we mentioned earlier. You can apply weights to maybe this square foot in front of him has more weight because they can much easier get to it than say backpedaling, for example. So that's a great way to get an idea of basically spatial awareness relationships between players, and then that can be a new variable in a predictive model as well. So there's a lot that can be extrapolated from this. So. It looks like we're up on time, but again, just want to thank all of you. We'll stick around for any questions, so thank you. Appreciate it.